In this video, we are doing practice problem 10 for 1D motion. It is a problem that deals with what happens when acceleration isn't constant. How do you deal with that? And of course, as you will remember from the lectures, we do it by integration, kind of the same way we generated our kinematic formulas in the first place. So let me show you practice problem 10. I don't think I have it set up yet. Pause recording for a moment. I'll be right. All right, fixed. So here it is. Pardon me. The acceleration of a motorcycle is given by the acceleration along the x direction as a function of time is constant a times t minus constant b times t squared, where constant a is 1.5 meters per second cubed, and constant b is 0.120 meters per second to the fourth. The motorcycle is at rest at the origin at t equals 0. We have a bunch of givens. Let's get those pulled out. Ax as a function of t is a t minus bt squared, where a is 1.50 meters per second cubed, b is 0.120 meters per second to the fourth. We also get that x at t equals 0 is 0, and v at t equals 0 is 0. So we get our initial position and velocity, and we will be needing those. All right, part A asks, find its position and velocity as functions of time. So we want x as a function of t, and we want v as a function of t. All right, so here's what I've written down from all of that. It's exactly what I was reading out as we went through. Let's start with v. Why? Because acceleration is the derivative of velocity with respect to time. And we can simply separate and integrate there. So the integral from 0 to t of the acceleration dt will be equal to the integral from v0 to v of dv. And in this case, we have to plug in our a, which is at minus bt squared. All right, integral 0 to t, parentheses, at minus bt squared dt equal to integral v0 to v of dv. The result's pretty easy, so at dt, take the integral, you get a over 2 t squared minus bt squared dt, integrate that, we get minus b over 3t cubed. On the other side, we just get v minus v0. As a result, we now know that v as a function of t will be equal to a over 2t squared minus b over 3t cubed. v0 is 0, so we just throw a 0 in there for that part. Doesn't matter if we move it to the other side or not, it's 0. If we plug in for a, we get 0.75 meters per second cubed t squared. If we divide 0.12 divided by 3, that's going to be 0.040 meters per second to the fourth, t to the third. So I only had one little mistake. All right, that's half of part A. The other half is to consider that v is equal to dx dt, separate and integrate. So we're going to get an integral from 0 to t of our v function from above, dt equal to integral from initial position x0 to final position x of dx. All right, plugging in, integral from 0 to t, open parentheses, a over 2t squared minus b over 3t cubed, in parentheses dt, equal to integral from x initial to x dx. All right, integrating that's not particularly harder. A over 2t squared, we'll get a t cubed, we'll have to divide by another 3, we'll have a over 6t cubed. bt cubed dt, integrating that, we'll get a t to the fourth, and we'll have to divide by 4, so we now have b over 12t to the fourth. Since our starting point is 0, we don't get any of those terms in this case, which is nice. On the other side, we just have x minus x naught, which means x as a function of t will be equal to a over 6t cubed minus b over 12t to the fourth. Because, again, x naught was 0. So that will be equal to, let's see, 1.5 divided by 6. So divided by 3, okay, so it's going to be 0.25 meters per second cubed t cubed minus, and the next part's relatively easy, 0.010 meter per second to the fourth t to the fourth. And those give us the answers to part A. Let's take a look. There is a part B. Okay, part B says, calculate the maximum velocity it attains. Okay, so this is the point where you ask yourself a question from your calculus class. How do you minimize or maximize anything with respect to anything else? Well, you take the derivative with respect to the thing you're maximizing against, in this case time, and you set it equal to 0. And dv dt happens to be equal to acceleration, which means we already know the equation here. It's at minus bt squared. So we'll set that equal to 0. We'll move things across, so we get a times t is equal to b times t squared. This is kind of hinting that t equals 0 is a critical point, but if we look above at our equation for velocity that we derived in part A, if you put in t equals 0, you see you get v is 0. So it's not very interesting to us. We'll be throwing that one out. All right. That leaves us with a is equal to b times t, so a over b is equal to t. That will be the time when we attain our maximum speed. So let's find out what the value of that is. It will be 1.5 meter per second cubed divided by 0.12 meter per second to the fourth. So that's going to be a bit larger than 10, but less than 15. 1.5 divided by 0.12 is 12.5 seconds. All right, we can now take that 12.5 seconds and we can plug it back into our equation from part A. So 0.75 meter per second cubed t squared minus, what was it, 0.040 meter per second to the fourth t cubed. We'll put this in for our t and we'll get our answer. So 0.75 times 12.5 squared minus 0.04 times 12.5 raised to the third is 39.0625 meters per second. All the digits of precision we've been given here are kind of on the order of 3. There's actually a good reason to think we should be truncating it at 3 digits of precision, which would be, 39.1 meters per second. We haven't really necessarily had that conversation yet. Depends on which class you're taking with me. But appropriate precision would be around 39.1 meters per second. Okay. That's the end of an example of what to do if you have a non-constant acceleration. You simply apply calculus principles. It's not bad.